The universe keeps a secret chemical ledger. One entry for a rare form of hydrogen called deuterium does not add up. Think of deuterium as a cosmic fingerprint, a single clue left over from the Big Bang that should tell us everything about the density and fate of everything. Yet across the cosmos, its abundance is a mess of contradictions. This video is a detective story, and we are following that fingerprint through 30 unexplained cosmic crime scenes. By the end, you will see the universe not as a static painting, but as a chaotic, evolving chemical engine where the rules seem to change from one galaxy to the next. We will find it missing from where it should be plentiful, and shockingly abundant in places it should have been destroyed. Why does our own galactic neighborhood show a depletion, while comets from the deep freeze carry a different story entirely? What does this tiny isotope reveal about our own plan, its watery past, and even the potential for life on worlds we have not yet seen? The mystery of cosmic deuterium is a puzzle with 30 pieces, and none of them seem to fit. Are you ready to see how deep the cosmic ledger has been cooked? The cosmic ledger begins with a single, perfect number. In the first minutes after the Big Bang, the universe was a seething nuclear furnace. As it expanded and cooled, protons and neutrons fused into the first atomic nuclei. This process, called Big Bang nucleosynthesis, was a fleeting window. It lasted only a few minutes before the universe became too diffuse and cold for fusion to continue. Within that window, a specific amount of a heavy form of hydrogen, deuterium, was forged and then frozen into the fabric of spacetime. The math behind this is extraordinarily precise. By plugging in the known laws of physics, cosmologists can calculate exactly how much primordial deuterium should have been created. That number is not just a random fraction, it is a cosmic thermometer. The predicted abundance of deuterium tells us the density of ordinary matter in the entire universe. It is one of the most powerful predictions in all of cosmology, a direct fingerprint from creation itself. So, what is that number? The models tell us that for every 1 million atoms of regular hydrogen created in the Big Bang, there should be precisely about 26 atoms of deuterium. This is our baseline, the universe's original chemical signature. Now, here is where the mystery ignites. When astronomers point their telescopes into deep space, searching for this primordial signal, they do not find a uniform 26 parts per million. Instead, they find chaos. In some of the oldest, most pristine clouds of gas between galaxies, they measure values eerily close to that prediction, a triumphant confirmation of the Big Bang model. But look elsewhere, and the ledger is a mess. Within our own Milky Way, the deuterium abundance is lower, as if someone has been secretly spending this cosmic currency. In certain dense molecular clouds where new stars are born, the numbers plummet even further, yet, bafflingly, around some active supermassive black holes, the readings spike. We are not talking about small, experimental errors. These are variations by factors of 2, 3, or more across the cosmos. The universe's birth certificate says one thing, but its current chemical makeup screams another. This is the fundamental conflict. We have a perfect, elegant prediction from the dawn of time, and a messy, contradictory reality observed in the present day. Every deviation from that primordial 26 is a crime scene, a clue that something has happened to the deuterium in the 14 billion years since it was made. This perfect primordial number begins to blur the moment we look closer to home. Our own galaxy, the Milky Way, holds a secret chemical map, and deuterium is its most puzzling contour line. If the universe started with a uniform sprinkle of this heavy hydrogen, you would expect to find it evenly distributed across our galactic neighborhood. But that is not what we see. Instead, astronomers have mapped a clear and troubling gradient. Picture the Milky Way as a vast, spinning disk with a brilliant, crowded core. Out in the serene outskirts, in the galactic suburbs, measurements of deuterium come closest to that pristine Big Bang value. But as you travel inward, towards the dense, bustling downtown of stars and gas near the galactic center, the amount of deuterium steadily drops. It is as if someone has been systematically removing it along the way. The leading suspect in this cosmic theft is, ironically, the very engines of light and life, stars. The theory is elegant and devastatingly simple. Deuterium is a fragile isotope. The extra neutron in its nucleus makes it slightly heavier than regular hydrogen, but also more vulnerable. Inside the furnaces of stars, where temperatures soar to millions of degrees, deuterium nuclei are destroyed. They fuse into helium-3 almost instantly, long before the star even begins its main sequence life. Every star that has ever formed, from the smallest red dwarf to the most massive blue giant, has consumed a portion of the primordial deuterium in its birth cloud. Over billions of years, as generation after generation of stars have ignited across the galaxy, they have been steadily eroding this primordial resource. This process should naturally create a gradient, with more deuterium burned away in regions of intense star formation, like the galactic center, and more preserved in the quieter outer reaches. Yet here lies the enigma, the gap in our understanding. When scientists run sophisticated models of galactic chemical evolution, feeding in the known rates of star formation and stellar deuterium destruction, the predicted gradient is too shallow. The models suggest the depletion should be more gentle, more smoothed out across the galaxy, but the real observations show a steeper, more dramatic drop. The deuterium is disappearing faster than our best theories can account for. It is as if we have identified the thief, but the amount missing from the vault is greater than the thief could possibly have carried. This forces a profound question: what other process is at work? Could vast reservoirs of deuterium be hiding in a form we cannot yet detect, perhaps locked away in icy dust grains or cold molecular clouds that shield it from measurement? Or is there an unknown mechanism, a second cosmic destroyer, working alongside the stars to scrub this fingerprint from the inner galaxy? The gradient is not just a map, it is a silent witness to a history more complex than our stories allow. The trail of the missing deuterium leads us out of the galaxy and into the deep intergalactic void. Drifting towards the Milky Way are immense rivers of cold gas, known as high-velocity clouds. These are not part of our galaxy's disk. They are ancient, primordial structures falling in from the cosmic hinterlands. For astronomers, they are like time capsules. Having never been processed through the violent cycles of star formation, their chemical composition should be a perfect snapshot of the early universe. They should hold deuterium at its pristine, Big Bang abundance, that sacred 26 parts per million. Measuring these clouds offers a chance to check the universe's original recipe, uncontaminated by stellar furnaces. Yet when we take the measurement, the ledger once again refuses to balance. In some of these pristine clouds, the deuterium levels are indeed beautifully close to the primordial value. But in others, the signal is depleted. It is lower than it should be. This is not just puzzling, it is deeply unsettling. It suggests a flaw in our most basic assumption. We thought these clouds were pure, untouched fossils, but if they contain less deuterium, it means they are not primordial at all. They have been processed somehow. One leading theory is that these clouds are not simple, free-floating gas. They could be the shredded remains of ancient dwarf galaxies, torn apart by the Milky Way's gravity long ago. If those dwarf galaxies once hosted stars, then their gas would have been through the stellar deuterium-destroying cycle. What we are measuring as a pristine infall could actually be cosmic recycling, the galactic equivalent of finding a faded, reused parchment inside what we thought was a sealed scroll. Another possibility is even more intriguing. The depletion could be caused by the cloud's own journey, as these massive structures plow through the thin, hot gas that surrounds the Milky Way, a halo known as the circumgalactic medium. Their leading edges are getting cooked. This interaction could be stripping away the lighter, regular hydrogen more efficiently than the slightly heavier deuterium, or it could be triggering chemistry that locks deuterium onto dust grains, hiding it from our telescopes. Either way, the message is clear. The boundary between our galaxy and the void is not a clean line. It is a turbulent, chemically active frontier where the primordial fingerprint is being smudged even before it enters the galactic disk. This conundrum forces us to rethink how galaxies grow. We pictured a neat model of fresh, pristine gas falling in to fuel new stars, but the deuterium evidence paints a messier picture, one of constant mixing, recycling, and processing that begins far beyond the galaxy's visible edge. If we cannot trust the purity of the infalling gas, then where can we possibly find a clean sample of the early universe? But to find a truly pristine sample, we must look much farther back in time, using the universe's own natural telescopes. Billions of light years away, quasars act as cosmic lighthouses. These are the intensely bright cores of ancient galaxies, powered by voracious, supermassive black holes. Their light travels across the cosmos, through eons of expanding space, to finally reach our telescopes. On that long journey, it passes through countless clouds of neutral hydrogen gas floating in the vast intergalactic medium. Each cloud leaves a unique fingerprint on the light, a specific dark line in the spectrum called a Lyman alpha absorption line. Because the universe is expanding, light from more distant gas is stretched more, shifting each absorption line to a different position. The result is a breathtaking data set, a dense thicket of absorption lines at different wavelengths known as the Lyman alpha forest. For cosmologists, this forest is a time machine. By carefully dissecting these lines, they can measure the chemical composition of the universe when it was only a fraction of its current age. Hidden within this intricate pattern is a much fainter signature, the subtle spectral imprint of deuterium. Since deuterium is slightly heavier, its absorption line is minutely shifted from the hydrogen line. Finding it is like listening for a single, quiet instrument in a roaring symphony. When scientists succeed, they are measuring deuterium abundance from billions of years ago in gas that has never been near a star. These should be the ultimate primordial measurements, a direct check of the Big Bang's ledger from deep time. Yet the mystery only deepens here. The results from the Lyman alpha forest show a shocking amount of scatter. Along some lines of sight, the deuterium abundance aligns perfectly with the pristine Big Bang prediction. It is a beautiful confirmation, but along other lines of sight, gazing through different parts of the ancient cosmos, the measured deuterium is significantly lower. This is not a gentle gradient, it is a patchwork quilt of values. The debate over what this means is fierce. One camp argues this is likely an observational challenge. Untangling the deuterium signal from the dense forest of hydrogen lines is phenomenally difficult. Contamination from other elements or subtle shifts in the gas's temperature and motion could be fooling our instruments, creating the illusion of variation where none exists. Another, more thrilling possibility is that the scatter is real. It represents true cosmic variance from one region of the early universe to another. Perhaps the Big Bang was not perfectly uniform on these scales, leaving some patches slightly richer in deuterium than others. Or perhaps localized destruction processes were already at work, even in the intergalactic medium, long before galaxies fully formed. Could pockets of that ancient gas have been heated by the first bursts of star formation or early black holes, destroying deuterium in specific corridors of space? The Lyman alpha forest was supposed to provide clarity, a view back to a simpler time. Instead, it reveals a young universe that may have already been a complicated chemical battlefield, its primordial signature being erased in some places and preserved in others, for reasons we are only beginning to guess. This chemical detective story brings us right to our own front door. Our solar system is not floating in a typical part of the Milky Way. We reside inside a vast, irregular cavity known as the local bubble. It is a region of space about 1,000 light-years across, filled with incredibly hot, thin, million-degree gas. Surrounding this bubble is a cooler, denser shell of atomic material, the remnants of the cataclysm that formed it. Astronomers believe the local bubble was carved out by a series of massive supernova explosions between 10 and 20 million years ago. These stellar detonations swept up and compressed the surrounding interstellar medium, leaving behind the scorching cavity we now inhabit. This is our immediate cosmic environment, and when we measure the deuterium abundance within it, we find another glaring anomaly. The levels here are even lower than the already depleted galactic average. Our neighborhood is a deuterium desert, so what happened? The prime suspect is the same violent event that created our home. Those ancient supernovae did not just blow a hole in space, they fundamentally processed the gas. The titanic shockwaves would have heated the interstellar material to phenomenal temperatures, creating perfect conditions for destroying fragile deuterium nuclei. Furthermore, the turbulent mixing from multiple explosions could have churned the gas, dredging up material from deeper within the galactic disk where deuterium depletion is more severe, and blending it into our local environment. But there is a twist that complicates this simple story of destruction. Some researchers propose a more subtle thief, a process called isotopic fractionation. Imagine the local bubble not just as a hot cavity, but as a complex chemical filter. Deuterium, being slightly heavier than regular hydrogen, can behave differently. In certain conditions, it might more readily stick to the surfaces of tiny interstellar dust grains. As the supernova shockwaves blasted through, they could have swept away the lighter hydrogen gas, while the slightly heavier deuterium, clinging to dust, was left behind in the cooler, denser walls of the bubble. From our vantage point inside the hot interior, it would simply appear missing. We are not seeing a true destruction, but a cosmic sorting. This theory suggests our local bubble might not be uniformly poor in deuterium. It might just be hiding it in plain sight, locked away in the icy mantles of dust grains that now reside in the surrounding molecular clouds. This local depletion forces a profound and personal question. If our own stellar neighborhood has such a skewed chemical history, what does that mean for us? The gas and dust that eventually formed our sun and planets were sourced from this very environment. The deuterium fingerprint we carry is not a pristine cosmic signature, but a localized, processed relic. It means that to understand the true primordial abundance, we cannot even trust the chemistry of our own backyard. We must look far beyond the walls of our local bubble, a reminder that our solar system's story is written in the altered chemistry of a long-forgotten stellar catastrophe. The very stars that erase deuterium from the galaxy sometimes whisper a different story. Inside a star's core, the fate of deuterium is sealed in an instant. The moment temperatures climb above a mere 1 million degrees, this heavy hydrogen becomes fuel. A deuterium nucleus fuses with a regular proton to create a light isotope of helium, releasing energy in a flash. This reaction is so efficient that any deuterium in a star's birth cloud is consumed long before the star reaches the main sequence, within its first few 100,000 years of life. A star is a perfect deuterium destroyer, which is why its universal depletion makes perfect sense. Yet, astronomers peering into the atmospheres of certain giant stars have detected faint, puzzling traces of deuterium. How can this be? The answer lies in a cosmic sleight of hand. This deuterium is not surviving from the star's birth, it is falling in from above. These stars are often surrounded by disks of material or are pulling in gas from a companion star. That infalling gas still contains its primordial deuterium, and as it rains down onto the star's visible surface, or photosphere, it briefly reveals its chemical signature before being dragged into the furnace below. It is a fleeting glimpse of the pristine universe, a deuterium delivery caught in the act, showing us that destruction and delivery are two sides of the same cosmic coin. This dance of delivery becomes a planetary scale mystery when we look at our own solar system. If all the planets formed from the same swirling disk of gas and dust around the young sun, you would expect them to share a similar deuterium fingerprint. The reality is a chaotic jumble of ratios. Take Venus, Earth, and Mars. Measurements from probes reveal that Venus's thick atmosphere is enriched in heavy deuterium by a factor of 150 times compared to Earth's oceans. Mars shows an enrichment about 8 times greater than Earth's. Meanwhile, the gas giants Jupiter and Saturn have deuterium levels much closer to the estimated primordial value, and comets from the distant Kuiper belt and Oort cloud often show deuterium ratios double that of Earth's oceans, or even higher. This is not a uniform solar system. It is a chemical crime seen with wildly different evidence at every planet. The explanation lies in a combination of cosmic violence and delicate chemistry. During planetary formation, temperature was everything. Close to the young sun, in the hot inner solar system where the rocky planets formed, deuterium had a slight advantage. In chemical reactions occurring on the surfaces of dust grains in the protoplanetary disk, the slightly stronger bond in heavy water, a molecule where deuterium takes the place of hydrogen, made it a bit more likely to stick. This process, called isotopic fractionation, gave the inner disk material a small initial enrichment in deuterium. But the real drama came later. For a world like Earth, with liquid water oceans and a protective atmosphere, that initial deuterium signature was largely preserved. Venus and Mars tell stories of catastrophe. Scientists believe Venus once had vast oceans, but a runaway greenhouse effect boiled them away. As the water vapor rose into the upper atmosphere, intense ultraviolet light from the sun split the molecules apart. The lighter regular hydrogen escaped into space more easily, while the heavier deuterium remained behind, becoming more and more concentrated over time. This is why Venus's atmosphere is now a deuterium-rich desert. Mars, with its weaker gravity, likely lost its early atmosphere and surface water to space through a similar, slower process, leaving behind a surface enriched in the heavier isotope. The comets present an opposite and equally profound puzzle. These icy messengers from the outer solar system formed in the deep freeze, where temperatures were so low that the subtle chemical preference for deuterium should have been minimal. Their high deuterium ratios suggest they did not form from a well-mixed disk, but in isolated, cold pockets where exotic chemistry or the inheritance of even older interstellar ice from before the solar system's birth locked in a different signature. This means the water in your glass right now, the water that makes life on Earth possible, carries a specific deuterium ratio that is a unique blend. It is a mixture of the inner solar system's slightly enriched water, delivered by asteroids, and the highly enriched water bombarded onto the young planet by comets from the far reaches. Our oceans are a chemical palimpsest, a layered record of delivery and disaster, written in the language of a heavy hydrogen that stars strive to destroy, but that planets and comets conspire to preserve in 1,000 different ways. The story of deuterium is written not just in the light of distant stars, but in the stones that fall from our own sky. Among the most precious of these cosmic messengers are carbonaceous chondrites, primitive meteorites that are essentially frozen samples of the dusty disk from which our solar system formed. Locked within their dark, carbon-rich matrices are tiny mineral grains, some no larger than a speck of dust, and when scientists subject these grains to the most sensitive isotopic analysis, they uncover a staggering secret. The deuterium levels in these minerals are not just slightly elevated, they are astronomically high, enriched by factors of hundreds, even thousands, times above the average solar system value. This is not a gentle chemical preference. It is a screaming isotopic anomaly that defies everything we know about planetary formation. To understand the scale, picture Earth's oceans as the baseline. Their deuterium enrichment, a legacy of planetary processes, is about 8 times higher than the primordial gas of the solar system. The minerals in these meteorites blow that number away. We are talking about enrichments that reach 10,000% or more. Such extreme values could never have been produced in the warm, turbulent environment of the early solar nebula. The physics simply does not allow it. The only place cold enough and quiet enough for this kind of dramatic chemical sorting is the frigid emptiness of interstellar space, long before our sun was even a glimmer in a molecular cloud. This points to a profound conclusion. These microscopic grains are not solar system natives. They are interstellar stowaways. They formed in the dark, cold molecular clouds that drift between the stars, where temperatures hover just a few degrees above absolute zero. In that deep freeze, chemistry operates in slow motion on the surfaces of dust grains. Atoms and molecules freeze into icy mantles, and rare cosmic ray particles provide just enough energy to trigger unusual reactions. In these conditions, a subtle mass difference becomes a powerful driver. The heavier deuterium atom, with its extra neutron, forms slightly stronger chemical bonds than regular hydrogen. In the patient, billion-year chill of an interstellar cloud, this tiny advantage can snowball. Reaction by painstaking reaction, deuterium gets selectively incorporated into complex organic molecules, building up layer upon layer of extreme enrichment, until the ice coating a dust grain becomes a concentrated reservoir of heavy hydrogen. The meteorite, then, is a cosmic freezer truck. It captured these ultra-cold, deuterium-rich ices and organics, preserved them during the violent heating of the solar system's birth, and delivered them to us 4.5 billion years later. But while the where seems clear, the how remains one of the fiercest debates in astrochemistry. What specific chemical pathways could possibly create such monumental fractionation? One leading theory focuses on ion-molecule reactions in the nearly perfect vacuum of space. Here, charged atoms and molecules can react without the interference of collisions, and the theoretical yields for deuterium enrichment can be very high. Another points to the chemistry occurring on the icy surfaces themselves, where the tunneling effect, a quirk of quantum mechanics, might make reactions with deuterium proceed faster in the extreme cold than those with regular hydrogen. Yet even the best models struggle to replicate the extreme levels we see in the lab. This gap between theory and observation means we are missing a piece of the interstellar chemical engine. Could there be unknown catalytic surfaces on cosmic dust, or periods of gentle warming and cooling that amplify the effect? The minerals in these meteorites are a direct telegram from the dark, cold nurseries of chemistry that existed before our Sun. They tell us that the raw ingredients for planets, and perhaps even life, were not blended uniformly. They were pre-processed in the galactic dark, imprinted with a heavy hydrogen signature so strong it survived the inferno of planetary birth. Every one of these ancient stones is a vault, holding a chemical memory of deep space that is far more dramatic and far more mysterious than we ever imagined. These microscopic meteoritic grains tell us of a cold, patient chemistry in deep space, but to see that chemistry in action, we must look at the clouds themselves. Drifting through the galactic arms are vast, wispy structures known as diffuse interstellar clouds. They are the tenuous gas between the stars, not dense enough to collapse into new suns, but far from empty. Within them, a subtle chemical ballet is constantly playing out. Atoms meet and form simple molecules on the surfaces of dust grains, all under the faint glow of distant starlight. For deuterium, these clouds are a critical waypoint. This is where it should transition from its free atomic form into molecules, primarily as hydrogen deuteride, a simple molecule where one hydrogen atom is replaced by its heavier cousin. Scientists have built intricate models of this astrochemical dance. They plug in the known density of these clouds, the cosmic ray flux that drives reactions, the temperature, and the theoretical rates at which atoms stick to dust grains and find each other. These models spit out a prediction, a precise ratio of how much deuterium should be locked away in molecules like hydrogen, deuteride, versus how much should remain as free atoms drifting in the gas. It is a beautiful, self-contained calculation of cosmic chemistry, and yet, when astronomers point their radio telescopes at these diffuse clouds to measure the actual abundance of hydrogen deuteride, the numbers rarely match the prediction. Sometimes the observed molecular deuterium is lower than expected, as if the chemical reactions are inefficient or being interrupted. Other times, in a baffling twist, it appears higher, as if some unknown process is aggressively funneling deuterium into molecules. This discrepancy is more than a minor calibration error. It is a direct challenge to our understanding of the interstellar environment itself. The failure of these models suggests we are missing something fundamental about the cloud's true nature. Perhaps their structure is not as smooth and uniform as we assume. They could be riddled with microscopic clumps and turbulent filaments, creating pockets of higher density where chemistry accelerates in ways our averaged models cannot capture. Or the problem could lie in the chemistry textbooks themselves. The fundamental reaction rates we use, many measured in laboratories under ideal conditions, might not apply perfectly in the extreme vacuum and cold of a diffuse cloud. A slight error in how fast a deuterium atom sticks to a specific type of dust grain, or how easily it is released back into the gas, could throw the entire prediction off. There is even a more radical possibility that the clouds are not the pristine chemical laboratories we imagine. They could be constantly contaminated by the debris of nearby stellar winds or the shockwaves from ancient supernovae, injecting fresh atoms or destroying molecules in a chaotic cycle our static models do not account for. Every mismatched measurement of hydrogen deuteride is a quiet message from the interstellar medium. It tells us that the space between stars is not a simple, passive void. It is a dynamic chemical reactor with a complexity we are only beginning to map, where the fate of a primordial atom is decided by processes we have yet to fully see. The cold, diffuse clouds are a chemical prelude, a whisper of what is to come, but follow the trail of gas inward toward the true stellar nurseries and the chemistry crescendos. We arrive at the dense, dark cores of molecular clouds. These are the wombs of stars, frigid cocoons of gas and dust so thick they blot out the background starlight. Temperatures here plunge to just 10 degrees above absolute zero, a cold so profound it slows atoms to a crawl. This is the environment where the subtle mass difference of deuterium becomes a dominant chemical force. In this deep freeze, a fascinating process called deuterium fractionation takes center stage. The star player is a peculiar molecule known as DCO+. It is a simple ion, a carbon monoxide molecule where the carbon is bonded to a deuterium atom instead of hydrogen. In the extreme cold, the formation of this molecule is heavily favored. The reason is both elegant and counterintuitive. The main reaction pathway involves a hydrogen molecule, ion, grabbing a deuterium atom from another molecule. Because the deuterium bond is slightly stronger, the reaction releases a tiny bit more heat. In the warmth of a diffuse cloud, that extra energy is meaningless. But in the intense cold of a dense core, that minuscule energy release is a kingmaker. It makes the reaction with deuterium proceed faster, efficiently funneling the heavy isotope into molecules like DCO+. So, we expect to see these molecules become dramatically enhanced here, and we do. Radio telescopes mapping these cores light up with the signature of deuterated molecules. This is not a mystery in itself, it is a triumph of astrochemical theory. The true paradox emerges when we compare one stellar nursery to another. The level of enhancement is not uniform. It is a chaotic tapestry. In one dense core, DCO+ might be enriched by a factor of 100 compared to its normal counterpart. In another core that looks virtually identical in mass and density, just a few light years away, the enrichment might be a factor of 10,000. This wild variation is the dense core paradox. It tells us that the simple recipe of cold plus gas is not enough. The deuterium budget of a future solar system is being set by a hidden history we are only beginning to read. What invisible variables are at play? The age of the core is likely crucial. Deuterium fractionation is not an instant process. It is a slow chemical accumulation over hundreds of thousands of years. An older core has simply had more time to build up its deuterium-rich molecules. Dynamics are another hidden hand. Is the core quiet and static, or is it being gently stirred by internal turbulence or the magnetic fields threading through it? Stirring can mix in fresh gas that has not been fully processed, diluting the deuterium's signal. Most intriguingly, the very faint warmth of the cosmic background radiation, or the subtle heat from a nearby newborn star still buried in the gas, can tip the scales. raise the temperature by just 5 degrees, and the delicate chemical advantage that favors deuterium begins to evaporate. So each dark core is not just a future star, it is a unique chemical experiment. Its final deuterium enrichment is a frozen record of its thermal history, its dynamical past, and its precise age. This means that two stars born in different corners of the same giant cloud could inherit wildly different amounts of heavy hydrogen, setting the stage for planetary systems with fundamentally different chemical starting points. The dense cores show us that the universe does not mix its ingredients evenly. It is a patchwork chemist, and the signature it leaves in the ice and gas of a newborn solar system is as unique as a fingerprint. The deep chemical freeze of a stellar nursery is shattered by the violence of birth itself. As a dense core collapses to form a new star, it does not do so quietly. From the infant protostar, two colossal, focused beams of material erupt at nearly the speed of light, carving through the surrounding cloud like cosmic blowtorches. These are protostellar jets, and they are among the most powerful forces in the universe. For decades, astronomers saw them as purely destructive, engines of chaos that would vaporize any delicate chemistry in their path. Then, they pointed specialized telescopes at the jets, looking for the spectral signature of water. What they found was not just water, but water screaming with deuterium. The levels of heavy water in these jets were hundreds of times higher than anything seen in interstellar clouds, a staggering enrichment that defied every expectation. This was the protostellar jet surprise. How could a molecule so fragile, carrying a heavy isotope so easily destroyed, not only survive but actually thrive in a million-degree plasma beam blasting away from a newborn star? The heat near the protostar should have annihilated every deuterium bond instantly. The discovery turned our understanding of these jets upside down. They were not just wrecking balls, they were chemical factories. The leading theory to explain this paradox is a story of cosmic theft and rapid delivery. It suggests the deuterium-rich water does not form in the hot jet at all. Instead, it is manufactured in the frigid, outer regions of the swirling disk of material that surrounds the baby star. Out there, in the permanent shadow where temperatures are just a few tens of degrees above absolute zero, the same slow, cold fractionation processes we see in dark clouds operate with incredible efficiency, building up massive reservoirs of heavy water ice on dust grains. Then, the violent dynamics of the star's birth intervene. The powerful magnetic fields that channel the jets can also reach out into these cold outer disk regions. They act like a cosmic catapult, grabbing chunks of this deuterium-enriched ice and flinging them into the jet stream almost instantly. The ice is sublimated into gas by the shock of acceleration, but the journey is so fast that the molecules do not have time to be destroyed by heat before they are launched far out into interstellar space. We are not seeing chemistry in the jet, we are seeing a high-speed delivery of pre-made, deuterium-rich material. However, an alternative, even more thrilling idea exists. Perhaps the jets themselves are the factories. As the supersonic jet rams into the slower-moving gas of the surrounding cloud, it creates a violent shock front. These shocks are not just simple heaters, they are complex environments where densities and temperatures spike in chaotic ways. In the turbulent wake of a shock, conditions might briefly become just right for a special kind of rapid chemistry. Ions and atoms slammed together with incredible force could form water molecules directly in the gas phase, and the unique physics of the shock might preferentially incorporate deuterium, mimicking the cold process, but at a breakneck pace. This shock chemistry would mean the jets are not just transporters, but active creators, forging heavy elements in their own fiery hearts. The protostellar jet, surprise, forces a profound realization. The most violent events in star formation are not dead ends for chemistry. They are its great distributors. They are the universe's way of seeding the raw, deuterium-enriched ingredients for water, and perhaps for life, far beyond their point of origin. Every jet from every newborn star might be spraying the galaxy with the heavy, frozen seeds of future oceans. This cosmic distribution system of heavy water faces its ultimate test in the icy wanderers of our own solar system. Comets have long been heralded as the pristine archives of the early solar system, frozen time capsules that should tell a single, coherent story of our origins. Their water, we believed, would carry a uniform chemical signature, a direct record of the conditions in the cold outer disk where they formed. That simple, elegant story has completely shattered. The reality is a cometary diversity head-scratcher that upends our planetary formation models. Take the majestic comets from the distant Oort cloud, like the spectacular Hale-Bopp. When astronomers measured their water, they found deuterium levels roughly double that of Earth's oceans. This seemed to fit the old picture perfectly. These comets formed far from the Sun, in a deep freeze that allowed for significant deuterium enrichment, and they were delivered to the inner solar system unchanged. But then came the detailed visit to Comet 67P, Churyumov-Gerasimenko, a comet from the Kuiper belt just beyond Neptune. The Rosetta spacecraft spent years orbiting this icy world, and its instruments made a startling discovery. The deuterium ratio in 67P's water was not high. It was remarkably close to the value found in Earth's oceans. How could two comets, both from the cold outer reaches, carry such dramatically different fingerprints? This single measurement forced a radical rethink. It means comets are not simple, homogeneous snowballs. They are amalgamations, cosmic rubble piles assembled from material that originated in wildly different parts of the protoplanetary disk. The early solar system was not a static, neat set of concentric rings. It was a dynamic, churning maelstrom. Powerful gravitational nudges from the giant planets, especially Jupiter, likely stirred the disk like a colossal spoon. This turbulence could have flung material from the warmer, deuterium-poor inner regions out to the frigid edges where comets were coalescing. Conversely, some material from the ultra-cold, deuterium-rich outer fringe might have been dragged inward before being incorporated into a growing comet nucleus. Each comet, then, is a unique archaeological dig. Its final deuterium ratio depends on the specific blend of ingredients it managed to sweep up. A comet like 67P might have formed from a recipe dominated by material that originated closer to the Sun, material that had experienced warmer temperatures and less deuterium fractionation before being scattered outward. An Oort cloud comet, by contrast, might be built mostly from the untouched, super-enriched ices of the solar system's farthest frontier. This diversity challenges more than just comet formation. It strikes at the heart of our own story. For decades, a leading theory suggested that Earth's oceans were delivered primarily by a bombardment of deuterium-rich comets. The match with 67P's water throws that narrative into question. If some comets carry water like ours, and others do not, then the source of our water becomes a complex puzzle. Perhaps it was not a single type of object, but a mixed delivery from both asteroids and a specific family of comets that formed in a particular zone of the disk. The comets are telling us that the solar system's birth was a story of immense and chaotic mixing, where the chemical identity of a world was determined by a lottery of location and motion, leaving behind a family of icy siblings that bear only a faint and confusing resemblance to one another. The chaotic mixing that built our solar system left its signature on the strangest world of all, Saturn's shrouded moon Titan. While comets and planets tell one story, Titan's thick, orange atmosphere writes its own chemical mystery in the language of methane. The Cassini spacecraft spent years studying this alien world, and its instruments revealed a startling fact. The methane in Titan's air is not like the methane we know. It is heavily enriched in deuterium, with a deuterium to hydrogen ratio several times higher than what we find in Earth's natural gas or even in most comets. This single measurement transforms Titan from a distant curiosity into a critical piece of the deuterium puzzle. Methane is a simple molecule, just one carbon atom bonded to 4 hydrogens. On Titan, it plays the role that water does on Earth, cycling through clouds, rain, rivers, and vast lakes. But methane is also fragile. The harsh ultraviolet light from the sun constantly breaks it apart in the upper atmosphere, a process that would strip Titan's air of all its methane in just tens of millions of years, a blink in the moon's 4.5 billion-year history. The fact that Titan still has a methane-rich atmosphere today means it must be constantly replenished. The source of that replenishment holds the key to the deuterium anomaly, and each possible source tells a radically different story about Titan's history. If the methane is primordial, bubbling up from a deep, ancient reservoir that has been locked inside Titan since its formation, then its high deuterium level is a fossil. It would mean the moon formed from material that was already incredibly enriched in heavy hydrogen, perhaps from the ultra-cold outer fringes of the Saturnian nebula, where fractionation ran wild. This would paint Titan as a perfectly preserved time capsule, its atmosphere a direct sample of the solar system's earliest chemistry. A second possibility points the finger outward, toward cometary delivery. Perhaps Titan's methane did not come from within, but was brought by a relentless bombardment of icy comets over billions of years. This would require that the comets striking Titan had an exceptionally high deuterium signature, even higher than the Oort cloud comets we have measured. It would suggest Titan's atmosphere is not native, but an accumulated layer of cosmic fallout, a testament to a violent past of celestial bombardment. The third and most compelling theory is that Titan is alive, geologically speaking. The moon may hide a global subsurface ocean of liquid water, laced with ammonia, sloshing beneath a shell of ice. In this dark, cold sea, chemical reactions between water and rock, known as serpentinization, could be continuously producing methane. This methane would then slowly seep up through fractures in the ice to refresh the atmosphere. But here is where the deuterium clue gets truly fascinating. If the methane is made in a water ocean, its deuterium level should match that of the ocean's water. Water, as we have seen, naturally fractionates. Over time, as methane is produced and lost to space, the ocean's water would become progressively heavier in deuterium, and so would the new methane being made. Cassini's measurement of Titan's present-day methane, then, could be a window into the current deuterium content of a hidden alien sea. Each source, primordial reservoir, cometary bombardment, or underground factory, imprints a different deuterium fingerprint and implies a different fate for this cloudy world. The high deuterium enrichment we see today tilts the scales. It suggests a long, complex history of loss and renewal, favoring a scenario where methane is being made from an evolving water reservoir, a process that has been running for billions of years. Titan's atmosphere is not just a weather system, it is the exhaust pipe of a hidden world, and the heavy hydrogen in its methane is a coded message about oceans we may never directly see. That hidden ocean on Titan is a ghost, a world we infer from chemical whispers. On Venus, the ghost is far more vivid, and its haunting signature is etched in the atmosphere with brutal clarity. Venus today is a hellscape, a world choked by clouds of sulfuric acid under a crushing carbon dioxide sky, with surface temperatures hot enough to melt lead. Yet, its atmosphere holds a profound chemical tombstone. The deuterium to hydrogen ratio there is not just high, it is staggering. It is over 100 times greater than the ratio found in Earth's oceans. To understand what this number means, picture a planetary-scale crime scene where the victim has vanished, and only the heaviest evidence remains. The leading theory is both elegant and tragic. Scientists believe Venus was not always this way. In its youth, it may have been a twin to Earth, complete with vast, shallow seas of liquid water. For perhaps hundreds of millions of years, it could have been a temperate, watery world. But something went catastrophically wrong. A runaway greenhouse effect took hold. As the planet warmed, those oceans began to boil. Water vapor, a potent greenhouse gas itself, flooded the atmosphere, trapping more heat and boiling the oceans faster in a vicious, self-reinforcing cycle. Eventually, the surface temperature soared, and all the liquid water was gone. But the story does not end with evaporation. In the upper atmosphere, intense ultraviolet light from the sun broke the water vapor molecules apart, splitting them into hydrogen and oxygen. The light, regular hydrogen atoms, moving at high speeds, could achieve escape velocity and bleed off into space. The heavier deuterium atoms, however, were less likely to reach that escape speed. They were left behind, accumulating in the atmosphere like salt in an evaporating pan. Over billions of years, this process, called hydrodynamic escape, acted as a giant planetary filter. It let the light hydrogen slip away while the heavy deuterium remained. The current extreme enrichment is the result, a direct measure of how much water has been lost. The deuterium is the residue of a vanished ocean. The mystery, however, is not in the what, but in the how much and the how fast. That 100 times enrichment is a clue, but translating it into a precise volume of lost water is incredibly difficult. It depends on the exact mechanics of that ancient escape process, which we do not fully understand. Was the loss a slow, steady trickle over billions of years? Or was it a violent, geologically rapid event, a cataclysmic atmospheric stripping that occurred in a relatively short window? The answer changes everything about Venus's potential for past life. A slow loss implies a long-lived, stable ocean, a potential cradle for biology. A fast, early loss suggests the window for life may have been brutally short. The complexity lies in the fact that escape is not a simple one-way street. Other processes complicate the ledger. Could volcanic outgassing over the eons have added new water with a different deuterium signature to the atmosphere, muddying the signal? Did massive asteroid impacts blast significant amounts of both hydrogen and deuterium into space, altering the ratio in ways we cannot easily calculate? Each of these factors adds a variable to an already fiendish equation. So, while the deuterium on Venus stands as the strongest evidence we have for a lost habitable world, it is also a locked diary. We can see the cover, We know it holds the story of a great flood that once was, but the precise chapters, the timeline of the tragedy, remain written in a language of atmospheric physics we are still struggling to decode. The ghost of Venus's ocean is real, but its true scale and its final, gasping breath are secrets still kept by the heavy hydrogen it left behind. Mars holds its own deuterium ghost story, written in the thin air and the frozen poles. The atmosphere of the red planet reveals a deuterium to hydrogen ratio about 8 times richer than Earth's oceans, a clear signpost of catastrophic water loss. With its weaker gravity, Mars could not hold onto the lighter hydrogen atoms as they were liberated from broken water molecules by solar radiation. Over eons, the hydrogen escaped to space, leaving the heavier deuterium behind as a concentrated residue. This simple ratio tells us a vast amount of water is gone, but it is a single number, a summary of a multi-billion-year tragedy. To understand the plot, we need to read the chapters in order, and for that, we look to the ice. The north and south polar caps of Mars are not simple sheets of frozen water. They are intricate layered deposits, towering stacks of ice and dust built up over millions of years, like the rings of a gargantuan tree. Each layer is a snapshot of the Martian climate when it fell, preserving within it a specific deuterium signature from that era. This polar layered deposit riddle is our best chance to reconstruct the history of Martian water, season by ancient season. The logic seems straightforward. Drill down through the layers, measure the deuterium at each depth, and you will have a timeline. A layer with very high deuterium would represent a period of intense water loss, when the atmosphere was heavily filtered. A layer with lower deuterium might indicate a calmer, wetter period, or perhaps a time when new water was released from volcanoes or subsurface reservoirs, diluting the signal. It is a climate history book written in ice, but when scientists begin to decipher it, they find the chapters are not in order. The variations in deuterium with depth are complex and non-linear. They do not show a simple, smooth increase from the bottom to the top, which you would expect if water loss was a steady, relentless process. Instead, the record is a jagged series of peaks and valleys. A deep layer might show a surprisingly high deuterium spike, while a layer above it, deposited much later, shows a lower value. This scrambling of the signal is the core of the riddle. It tells us that Mars did not lose its water in a simple, linear fashion. The process was episodic, chaotic, and deeply intertwined with the planet's wild climate swings. The causes of these dramatic shifts are written in the dust mixed with the ice. Mars's tilt on its axis is unstable, wobbling far more dramatically than Earth's over cycles of hundreds of thousands of years. When the tilt is high, the poles receive more sunlight, causing ice to sublimate and move toward the equator. When the tilt is low, the poles are in perpetual deep freeze, accumulating new layers. Each of these climatic extremes would leave a different deuterium fingerprint in the newly deposited ice. A period of high tilt and sublimation might enrich the atmospheric deuterium quickly, which then gets locked into the next layer that forms when the climate shifts again. But other forces are at play, muddying the record. Global dust storms, which engulf the entire planet, can radically alter atmospheric chemistry and water transport, potentially resetting or overwriting the deuterium signal in a single event. Even the source of the water matters. If an ancient subsurface aquifer burst to the surface in a massive flood, it would inject a large volume of water with a different, possibly lower, deuterium ratio into the system, temporarily changing the atmospheric balance before it was lost again. Reading the polar layers is like trying to reconstruct a symphony from a recording that has been sped up, slowed down, and had other songs mixed in at random intervals. The deuterium is the melody, but the rhythm and the key keep changing without warning. This means the exact timing of Mars's major water loss events and what triggered each one remains frustratingly unclear. Did most of the water vanish in a dramatic early catastrophe, or has it been slowly bleeding away in fits and starts until today? The polar deposits hold the answer, but in a language we are still learning to translate, a testament to a world that did not die quietly, but in a series of turbulent, frozen gasps. The ghost oceans of our solar system are not all lost to time. Beneath the cracked, icy shell of Jupiter's moon Europa, scientists are almost certain a vast, global saltwater ocean sloshes in perpetual darkness. It is a world sealed away under miles of ice, kept liquid by the relentless gravitational kneading of Jupiter's tides. This hidden sea is one of the most promising places to search for life beyond Earth, but to understand its story, we need a chemical key. That key is its deuterium ratio. If we could somehow plunge a probe through the ice and taste that alien water, what would we find? The deuterium value locked in Europa's ocean would be a direct message about the Moon's deepest history, and it could point to one of three radically different origins. The first possibility is a primordial fingerprint. Europa formed in the frigid outer solar system, in the shadow of giant Jupiter. If its ocean water was sourced directly from the icy planetesimals that built the Moon, and if that ice has never been significantly processed or recycled, then the deuterium ratio could be very high. It might match the extreme values we see in some comets from the Oort cloud, a relic of the ultra-cold chemistry from before the solar system's birth. This would paint Europa as a perfectly preserved ice museum, its ocean a time capsule of the ancient materials that came together to build the outer planets. A second, more dynamic story points to a cometary origin. Perhaps Europa's ocean was not born with the Moon, but delivered later. A heavy bombardment of icy comets over billions of years could have supplied the water. In this case, the deuterium ratio would be a complex average, reflecting the mix of comets that struck Europa. Given the diversity we see among comets, the value could be anywhere from moderately to extremely enriched. This would mean Europa's ocean is not native, but an accumulated gift, or perhaps a series of violent inheritances from the chaotic outer solar system. The third, and most geologically thrilling, scenario is a processed ocean. Europa is not a dead ice ball. Its fractured surface hints at a world of immense internal activity. If there is active hydrothermal venting on its seafloor, where hot rock meets water in a process called serpentinization, then the ocean is being constantly recycled and chemically altered. This ongoing geochemistry could fundamentally reset the deuterium's signature. Water interacting with hot rock might exchange hydrogen isotopes, driving the ratio toward a new equilibrium, one that reflects the internal workings of the Moon rather than its original ingredients. A processed ocean would be a living, breathing chemical engine, and its deuterium would tell us less about where Europa's water came from, and more about what is happening to it right now. This single number, therefore, is not just a measurement, it is a decoder ring for habitability. A primordial or cometary ocean, while fascinating, might be a stagnant, chemical dead end. But a processed ocean, one actively stirred by geothermal heat, is the kind of environment that could provide the energy and chemical gradients needed to sustain life, much like hydrothermal vents do in Earth's deepest seas. The Europa ocean enigma is a perfect example of how a tiny isotopic clue can hold the weight of an entire world's biography. For now, it remains a maddening unknown, a secret kept by 20 kilometers of ice. Every future mission designed to fly through its plumes or land on its surface carries with it the hope of finally reading this hidden message, of discovering whether that dark sea is a frozen archive, a cosmic collection, or a simmering, living kitchen. The search for alien oceans now leaps beyond our solar system into the light of distant suns. With instruments like the James Webb Space Telescope, astronomers have begun a new era, not just finding exoplanets, but tasting their atmospheres. They search for the chemical fingerprints of water, methane, and carbon dioxide. But the ultimate prize, the key to unlocking a world's deepest history, would be the detection of a deuterated molecule, like heavy water, in the air of another world. Finding it would be a monumental breakthrough, but interpreting its signal presence a theoretical challenge as vast as space itself. A single measurement of deuterium abundance from a gas giant or a rocky super-Earth would not come with an instruction manual. Instead, it would hand us a cosmic riddle with multiple, intertwined answers. That number would be a composite signal, a blend of the planet's birth, its journey, and its potential for harboring life. First, it could tell us about the planet's formation location within its protoplanetary disk. A very high deuterium ratio would scream that this world assembled in the cold, outer reaches of its system, where fractionation ran wild. A lower ratio would suggest it formed closer to its star, in a warmer environment where deuterium was less enriched. But planets are not static. We now know they often migrate, drifting inward or outward from their birthplaces due to gravitational interactions. A world orbiting close to its star, but showing a high deuterium signature, would be a smoking gun. It would tell a story of a dramatic migration, a planet born in the deep freeze that later journeyed to the inner warmth, carrying its icy chemical identity with it like a passport stamp. For a rocky planet in the habitable zone, the deuterium question becomes even more profound. Detecting heavy water in its atmosphere could point to the presence of a surface ocean. But is that ocean primordial, delivered by comets, or continuously replenished by geologic activity? A deuterium value matching certain comets might favor a delivery model. A different value, perhaps lower, could suggest the water is being processed and recycled from a planetary interior through volcanism and plate tectonics, a sign of a geologically active, and therefore more potentially habitable, world. We are standing at the very beginning of this detective story. Right now, we are still building the interpretive framework, the set of rules that will allow us to decode these future signals. Each new observation of a protoplanetary disk, each refined model of planetary migration, and every measurement from our own diverse solar system adds another piece to this grand puzzle. The day we first spot the spectral line of heavy water in an exoplan, its atmosphere will not be an end, but a magnificent and confusing beginning. The moment a single number from a distant star forces us to write entirely new chapters in the story of how worlds are born, move, and live. Deep within the cold, dark clouds, before a star even flickers to life, chemistry is already writing a recipe for worlds. These are prestellar cores, the gravitationally bound seeds of future solar systems, isolated pockets of gas and dust on the verge of collapse. They are the blank slates upon which a planetary system's chemical identity will be written. Yet when astronomers probe these cores with radio telescopes, they find the slate is not blank at all. It is already inscribed with a rich and complex chemical text, one where molecules like formaldehyde, methanol, and even more complex organics are already heavily loaded with deuterium. This discovery presents a profound inheritance problem. Did these deuterium-rich molecules form here, in the unique, dense environment of the core itself? Or were they simply inherited, fully formed, from the surrounding molecular cloud that birthed this core? The answer determines the very starting point of chemistry for every planet that might one day form here. Think of it as a cosmic nature versus nurture debate for molecules. The surrounding molecular cloud is a vast, diffuse chemical reservoir. Over millions of years, in its general cold and darkness, slow processes can build up deuterium enrichment in simple molecules. When a denser region within that cloud begins to contract under its own gravity to form a prestellar core, it pulls in that surrounding material. So, some of the deuterium signature we measure is undoubtedly an heirloom, a chemical dowry passed down from the parent cloud. But the core is not a passive recipient. As it condenses, its internal conditions change. The density increases, shielding the interior from external starlight and allowing temperatures to drop even further. This can trigger new and even more efficient deuterium fractionation reactions that were not possible in the thinner cloud. The core becomes its own chemical factory, potentially amplifying the deuterium signal beyond its inherited baseline. Disentangling inheritance from in situ production is a monumental challenge. It requires mapping not just the core, but the cloud around it with exquisite detail. Astronomers look for gradients. If the deuterium enrichment is uniform from the cloud into the heart of the core, it strongly suggests a simple inheritance story. But if the enrichment spikes dramatically right at the core's center, where densities are highest and conditions are most unique, that is a clear signature of local chemical activity supercharging the process. Early evidence points to a hybrid reality. Cores seem to start with an inherited level of deuteration from their parent cloud, a foundational chemical theme. Then, as they collapse and their internal engines start to hum, they compose new and more complex variations on that theme, creating an even richer deuterium symphony in the very place where planets will eventually coalesce. This means the chemical fate of a future solar system is not decided at the moment of planetary formation, but much earlier, in the quiet, cold gestation of the prestellar core, a hidden workshop where the universe prepares the heavy, complex ingredients for everything that comes next. These hidden chemical workshops are not always left in peace. Sometimes, the universe sends in the demolition crew. On the edge of vast stellar nurseries like the Orion Nebula, a violent frontier exists where the searing ultraviolet light from newborn, massive stars slams into the cold walls of a molecular cloud. This battleground is called a photodissociation region, a place where chemistry is driven not by cold and patience, but by pure, raw photon energy. The name itself tells the story: photodissociation, the breaking apart of molecules by light. In these intense zones, models predicted a clear, grim fate for delicate deuterated molecules. The harsh UV radiation should rip them apart, destroying the fragile bonds that hold the heavy hydrogen in place. Scientists expected deuterium fractionation to plummet here as the delicate cold chemistry is scorched away. The Orion bar, a bright, sharply defined ridge in the Orion Nebula, is one of the most famous and well-studied meteorites in the sky. It is a natural laboratory for testing these theories of radiation-driven destruction. Yet when astronomers pointed their most powerful telescopes at this cosmic firebreak, they found a puzzle. Instead of the expected drop, the measurements of certain deuterated molecules, like DCO+, showed stubborn enhancements. The levels of heavy hydrogen locked in molecules were off by significant factors from what the elegant models predicted. This is the photodissociation region puzzle. The harsh light is not simply erasing the deuterium's signature. It seems to be altering the chemistry in ways we did not anticipate. One compelling explanation is that the radiation is not just a destroyer, but a trigger for a new kind of rapid, violent fractionation. The intense UV light creates a soup of ions and free radicals, highly reactive fragments of molecules. In this chaotic, energetic environment, new reaction pathways open up. Some of these pathways might actually favor the incorporation of deuterium, even at higher temperatures, because they rely on different physics than the slow, cold processes. It is as if a wildfire, while consuming the forest, also creates the perfect, brief conditions for a new, hardier type of plant to sprout amidst the ashes. Another layer of complexity comes from the structure of the cloud itself. A PDR is not a clean, sharp wall. It is a turbulent, fractal-like transition zone, riddled with dense knots and filaments of gas that are partially shielded from the full brunt of the radiation. Within these tiny, shadowed pockets, the old, cold chemistry might still be chugging along, producing deuterium-rich molecules that then leak out into the brighter zones, confusing our measurements. Our models tend to treat these regions as smooth and uniform, but nature is gloriously clumpy. The discrepancy forces a humbling admission. Our understanding of how chemistry operates under extreme stellar radiation is still primitive. We are missing key reactions or misjudging the rates of known ones in this exotic environment. Solving the PDR puzzle is not just about deuterium. It is about accurately reading the chemical history of every star-forming region in the cosmos. These brilliant, harsh borders are where most of the light and complex molecules in galaxies are produced. If we cannot decode the chemistry here, in this visible, violent crucible, then our story of how the ingredients for life are forged and distributed across the universe remains fundamentally incomplete. The shockwaves that sculpt our local bubble are gentle ripples compared to the true titans of violence. When a massive star ends its life in a supernova, it unleashes a blast wave of energy that tears through the surrounding interstellar medium at thousands of kilometers per second. This is a supernova remnant, a chaotic frontier of shredded gas and searing radiation. For decades, these cosmic wrecking balls were seen as the ultimate destroyers of delicate chemistry. Any complex molecule, any fragile isotope like deuterium, would be instantly vaporized in the million-degree plasma. But nature, as always, defies simple categories. In the turbulent wake of these unimaginable blasts, a strange and counterintuitive chemistry may be struggling to life. The key lies in the shock front itself, a razor-thin boundary where the supersonic wall of debris slams into the cold, undisturbed gas ahead of it. This collision does not just heat the gas, it compresses it to incredible densities and creates a maelstrom of charged particles. In this violent soup, a process called spallation can occur. High-energy protons, accelerated by the shock, can smash into heavier nuclei like carbon, oxygen, or nitrogen that are floating in the interstellar gas. The impact is so violent, it chips pieces off the larger nucleus. Think of it as cosmic shrapnel, one of the fragments that can be blasted free in this subatomic collision is a deuterium nucleus. This is a radical idea. It suggests that in the most destructive environments in the galaxy, new deuterium could be forged, not in the vast quantities of the Big Bang, but in a slow, trickle production that adds a fresh signature to the interstellar ledger. Theoretical models show it is possible, but the yields are predicted to be vanishingly small. The real mystery is whether this trickle could ever be significant. Could the cumulative effect of countless supernovae over billions of years actually produce a measurable amount of new deuterium, subtly altering the chemical map of a galaxy? Or is this shock production just a fascinating footnote, completely overwhelmed by the far greater destruction of deuterium happening in those same stellar furnaces? We are left with a dizzying paradox. The same cataclysm that destroys a star and scours its neighborhood could also be a secret, sporadic factory for the universe's most fragile ingredient. It forces us to see these remnants not as barren wastelands, but as potential chemical reset buttons, places where the slate is wiped almost clean, but where a few heavy new words might be scrawled in the margins by the force of the blast itself. This slow trickle of shock-borne deuterium connects to a far more pervasive and controversial cosmic process. Racing through the galaxy at nearly the speed of light are cosmic rays, a relentless hail of atomic nuclei, mostly protons and helium. These are not gentle particles. They are subatomic bullets with energies that dwarf anything produced in our most powerful colliders, and when one of these bullets strikes a heavier atom floating in the interstellar gas, something remarkable can happen. The impact is so violent, it literally shatters the target nucleus, a process known as spallation. Fragments fly off, and among those fragments can be a newly minted deuterium nucleus. Here lies a tantalizing possibility. Could this constant, galaxy-wide bombardment of cosmic rays be a secret factory, producing deuterium right now and adding it back into the interstellar ledger? This is the cosmic ray spallation controversy, a fierce debate that cuts to the heart of whether deuterium is only a relic or an ongoing product of cosmic violence. The theory is elegant in its simplicity. We know cosmic rays exist, and we know the physics of spallation works. The math, however, tells a more complicated story. To see if this is a viable source, scientists must run a cosmic accounting exercise. They start by measuring the observed flux of cosmic rays, how many of these high-energy particles are passing through a given volume of space every second. Then, they calculate the density of potential target atoms, like helium, in the interstellar medium. Using known nuclear cross-sections, they can estimate the rate at which spallation events would occur. Finally, they tally the probable yield of deuterium from each collision. When all these numbers are crunched, the result is sobering. The calculated production rate from cosmic ray spallation is vanishingly small. It is a mere whisper compared to the thunderous destruction of deuterium happening inside stars. At best, it might account for a tiny, almost imperceptible, fraction of the deuterium we see. It cannot possibly explain the large-scale depletions or the dramatic enrichments we observe across the galaxy. For most astronomers, the case is closed. Cosmic ray production is a fascinating footnote, but not a major player in the deuterium mystery. Yet, the controversy persists for a profound reason. The debate is not really about explaining all of the missing deuterium. It is about the unsettling gaps in our own knowledge. That crucial first number in the calculation, the cosmic ray flux, is what we measure here in our own solar system, inside the protective bubble of the Sun's magnetic field. But is this the true, universal value? Cosmic rays are born in the most violent events in the galaxy, supernova remnants, pulsar wind nebulae, and perhaps even supermassive black holes. Their journey to us is not a straight line. They are scattered and deflected by the Milky Way's tangled magnetic fields. The flux we feel locally might be completely different from the flux in other parts of the galaxy, especially in the intense environments where they are born. What if, in the chaotic hearts of star-forming regions or near the galactic center, the cosmic ray flux is orders of magnitude higher than our local measurement? In those extreme pockets, spallation could become a significant local source, creating deuterium hotspots that skew the chemical map. The problem is, we cannot yet measure that directly. So the deuterium abundance in a specific cloud becomes a potential proxy, a chemical detective that might be pointing to an invisible torrent of cosmic rays we cannot otherwise see. This ties the fate of a tiny isotope directly to one of astrophysics' greatest unsolved puzzles, the origin of cosmic rays themselves. We do not know exactly how nature accelerates particles to such insane energies. If anomalous deuterium enrichments in certain clouds were conclusively linked to high cosmic ray flux, it would provide a revolutionary new tool. Deuterium would become a cosmic ray dosimeter, a permanent chemical record of where and when these particle barrages were most intense. A cloud with unexpectedly high deuterium might not just be a chemical anomaly. It could be a fossilized echo of a nearby supernova that happened millions of years ago, its shockwave now gone, but its particle legacy etched into the gas. The controversy, therefore, is a beautiful collision of scales. It connects the microscopic fate of a single atomic nucleus to the galaxy-spanning mystery of the most energetic particles in existence. While cosmic rays likely are not the master key to the deuterium puzzle, they remind us that every measurement is a snapshot in a dynamic, violent cosmos, where the ingredients of creation are still being churned and altered by forces we are only beginning to map. That cosmic ray controversy forces us to confront the limits of our vision. We can map the gas, we can count the stars, but what about the mass we cannot see? The story so far has been a chemical detective hunt through the visible universe. Yet, the cosmos holds a deeper secret, a shadowy architecture that underpins everything. For decades, we have known that the gravity holding galaxies together comes not from the stars and gas we see, but from something else, something dark and invisible. This dark matter makes up over 80% of the universe's mass, a silent giant shaping the cosmos from the shadows. Its nature is the greatest unsolved puzzle in physics. But what if this ghostly substance, through some unknown interaction, is also a ghost in the chemical machine? Could dark matter be subtly influencing the deuterium abundance we struggle to explain? This is not mainstream science. It is a speculative frontier, a whisper from the theoretical edge. Yet the idea is too compelling to ignore. Some highly exotic models propose that dark matter is not completely inert. The particles that constitute it might occasionally decay or annihilate one another. If that happens, the event would release a burst of energy, or perhaps inject new, fast-moving particles like protons or electrons into the surrounding gas. Imagine a hidden, universe-wide background of these faint, dark explosions, popping off silently throughout galactic history. The energy from these events would be minuscule compared to a supernova, but it would be pervasive, a gentle, universal heating. In the cold, delicate environments of molecular clouds, where deuterium fractionation is a game of thermodynamic subtlety, even a tiny, extra source of heat could be a game-changer. It could raise the temperature just enough to slow down or alter the chemical pathways that favor deuterium, subtly shifting the enrichment levels we expect. More dramatically, if the annihilation products include particles like antiprotons, they could collide with normal matter and trigger nuclear spallation, potentially creating new deuterium right there in the cold cloud, in a way completely divorced from cosmic rays or stellar processes. The signature would be a pattern, a specific map of deuterium abundance that aligns not with star formation regions, but with the predicted distribution of dark matter in a galaxy. We would look for places where the deuterium levels are inexplicably high or low in the quiet, dark outskirts of a galaxy, precisely where dark matter is thought to dominate. Finding such a correlation would be revolutionary. It would mean that deuterium is not just a fossil of the Big Bang or a product of stellar processing. It would be a living chemical tracer, a beacon illuminating the interactions of the universe's dominant, unseen component. It would be our first tangible clue that dark matter does something more than just exert gravity. For now, this remains a beautiful speculation, a long shot woven from mathematics and hope. No observation has yet demanded such an exotic explanation. But the very fact that we can ask the question, that a tiny isotope of hydrogen could theoretically serve as a bridge between the visible chemistry we understand and the dark universe we do not, is a testament to how deeply interconnected cosmic mysteries can be. The deuterium in a distant cloud might be holding a message written in the language of shadows, waiting for the day we learn how to listen. Every star leaves a chemical legacy in its wake. When a massive star explodes, it seeds the surrounding gas with heavy elements forged in its core, from carbon and oxygen all the way up to iron. Astronomers call this enrichment metallicity, a measure of everything in the universe that is not hydrogen or helium. It is the fingerprint of stellar processing. Since stars are also the primary destroyers of deuterium, logic dictates a simple, inverse relationship should emerge. Gas that has been through many cycles of star formation, gas with high metallicity, should be severely depleted in deuterium. Pristine gas with low metallicity should retain its primordial bounty. This expected correlation is a cornerstone of galactic chemical evolution models. It should be a clean, downward-sloping line on a graph. Yet when we plot the actual data from stars and gas clouds across the Milky Way and beyond, we get a scatter plot of chaos. The relationship is there, but it is blurred, messy, and filled with outliers. This variation with metallicity is not a failure of the theory, it is a revelation. That messy scatter is the universe's way of recording its own turbulent history, a chemical diary written in a language of inefficiency and galactic winds. The imperfect correlation tells us that star formation is not a perfect destroyer. It is a leaky, uneven process. In some regions, star formation might be so bursty and intense that it rapidly depletes both deuterium and enriches the gas with metals, creating a strong correlation. In other, quieter galactic suburbs, star formation proceeds slowly. Deuterium is destroyed gradually, and metals are produced and mixed into the gas in a less synchronized way, smearing out the expected link. But the real story is told by the gas that escapes entirely. Galactic winds, driven by supernova or the intense radiation of massive stars, can blast enriched, metal-heavy material out of a galaxy's disk and into its halo. This wind carries away the very metals that should correlate with deuterium destruction, effectively decoupling the two processes. The deuterium poor gas left behind might now be missing the high metallicity signature we expect because the metals have been violently ejected. Conversely, a galaxy might accrete fresh, low metallicity gas from the cosmic web after a period of intense star formation. This new gas dilutes the metal content but does nothing to restore the destroyed deuterium, again scrambling the expected pattern. So that messy graph is not a problem to be solved, it is a complex portrait to be interpreted. Each data point is a snapshot of a local environment's unique balance between creation, destruction, and escape. A region with surprisingly high deuterium but moderate metallicity might be a site of recent gas infall. A pocket with very low deuterium and surprisingly low metallicity could be an area where a galactic wind recently stripped the metals away, leaving behind the ghost of stellar processing without the chemical evidence. This means we cannot use metallicity alone as a simple gauge for how much deuterium a cloud should have. We must read it as one chapter in a much longer story of a galaxy breathing in fresh gas and breathing out enriched winds, a story where the chemical ledger is never fully balanced, and where the fingerprint of the Big Bang is erased in fits and starts, not with a single, elegant stroke. The first dawn of starlight was a cosmic catastrophe. After the primordial darkness of the universe's first few 100 million years, the ignition of the first stars and galaxies did not just bring light, it brought a searing, sterilizing flood of ultraviolet radiation. This was the epoch of reionization, when those early ultraviolet photons ripped electrons from the neutral hydrogen atoms that filled all of space, transforming the universe from an opaque fog into the transparent void we see today. It was a fundamental phase change for the cosmos, and for any fragile atom caught in that first glare. Deuterium, with its slightly stronger bond, is marginally harder to break apart than regular hydrogen. But in the face of that all-pervasive ultraviolet onslaught, that small advantage would have meant very little. Theoretically, that first starlight could have destroyed deuterium on a staggering, universal scale, selectively burning away the heavy hydrogen from the intergalactic gas. This epoch, then, should have cast a long shadow, a permanent dip in the deuterium abundance that we might still read in the oldest gas clouds today. The hunt for this reionization shadow is a search for a ghostly echo from the universe's first sunrise. Astronomers look to the most distant quasars, whose light passes through the ancient gas that was once bathed in that primordial ultraviolet glow. They search for a subtle, systematic drop in the deuterium signal in gas from that specific era, a chemical scar left by the first starlight. The challenge is that the signal they are looking for is incredibly faint, buried within the already complex and noisy data of the Lyman alpha forest. Current telescopes and instruments are pushing at the very edge of their capabilities. Some analyses hint at a possible, slight depletion in deuterium at the highest redshifts, the farthest look-back times. But the results are not yet conclusive. The scatter in the data is still too great, the systematic uncertainties too large, to say definitively whether the shadow is really there. It could be that the effect was more localized, that the ultraviolet radiation from the first galaxies was patchy, creating a mottled pattern of deuterium destruction rather than a clean, universal shadow. Or perhaps the destruction was so complete in certain filaments of gas that those regions became invisible to our current methods, leaving us with a biased sample that survived. This mystery sits at the precipice of our observational reach. It ties the fate of a single isotope directly to the most transformative event since the Big Bang itself. To solve it, we need more than better data. We need a deeper understanding of how those first galaxies actually lit up. Did they flicker on gradually, or in a sudden, brilliant burst? Was their light soft or harsh? The deuterium abundance in the most ancient gas could be the ultimate calibrator, a chemical fossil that records the intensity and timing of the universe's very first dawn. Until we can measure it with certainty, the shadow of reionization remains a tantalizing silhouette, a hint that the universe's childhood was written not just in light, but in the heavy hydrogen it left behind or failed to destroy. Supercomputer simulations of our universe are staggeringly complex digital twins. They begin with the smooth, near-uniform conditions just after the Big Bang, seed them with the tiny fluctuations we see in the cosmic microwave background, and then let the laws of physics play out across billions of virtual years. Gravity pulls matter into filaments and halos, gas cools and collapses, stars ignite and explode. These simulations can recreate the grand architecture of the cosmic web, the majestic spiral arms of galaxies, even the distribution of dark matter. Yet, when it comes to the chemical map of a single, tiny isotope, they consistently fall short. This is the numerical simulation shortfall, and it is a humbling reminder that the devil and the deuterium is in the details. The models struggle to reproduce the messy, contradictory map of deuterium abundance we actually observe in our Milky Way and beyond. They tend to err in one of two frustrating directions. In some simulations, the gas within a virtual galaxy mixes too efficiently. Powerful currents stirred by supernova blasts and galactic rotation churn the primordial gas from the outer halo with the processed gas in the inner disk far too quickly. This overmixing dilutes and destroys deuterium uniformly, creating a galaxy that becomes deuterium poor everywhere, far faster than we see in reality. It fails to produce the strong, persistent gradient from the rich outskirts to the depleted center that our telescopes clearly map. Other simulations have the opposite problem. Their virtual galaxies are too placid. The gas mixes too slowly, leaving sharp, segregated boundaries between different reservoirs. In these models, pockets of pristine, deuterium-rich gas survive improbably long in the bustling galactic downtown, defying the clear observational evidence of severe depletion near the core. Both failures point to the same fundamental gap. Our simulations are missing, or misrepresenting, the small-scale physics that governs the real cosmic kitchen. The most critical missing ingredients are turbulence and stellar feedback. Turbulence is not just a gentle stirring, it is a chaotic, multi-scale cascade of energy, from the vast motions of spiral arms down to is smaller than our solar system. This turbulence determines how quickly fresh gas mixes with old, how effectively clouds are shredded or compressed, and ultimately, how fast deuterium is delivered to the stellar furnaces that will destroy it. Our simulations simply cannot resolve these tiny, violent swirls, so they approximate their effects with broad brush rules that often get the recipe wrong. Even more crucial is stellar feedback. This is the collective term for how stars give back to their environment. It includes the gentle pressure of starlight, the steady stream of stellar winds, and the cataclysmic force of supernova. Feedback is the galaxy's self-regulating mechanism. It heats gas, drives winds, and prevents too many stars from forming too quickly. In the context of deuterium, feedback is the primary destroyer and distributor. A supernova does not just burn deuterium in its immediate vicinity. Its shockwave can eject enriched material out of the galactic disk entirely, or trigger the collapse of a new, deuterium-rich cloud elsewhere. Getting the timing, energy, and location of these feedback events correct is everything. If a simulation injects supernova energy too smoothly or in the wrong places, it fails to create the observed patchwork of depletion and preservation. The deuterium shortfall, therefore, is not a failure of cosmology. It is a precise diagnostic tool. It tells us that our digital universes are still too coarse, too clean. The real cosmos is a gritty, chaotic place where energy is injected in sudden, localized explosions, and where gas flows in a fractal cascade of structure we are only beginning to appreciate. Every mismatch between a simulation's deuterium map and the real one is a signpost, pointing directly at the physics we need to understand better. To solve the mystery of this heavy hydrogen, we must first teach our computers how to properly simulate the universe's beautiful, messy, and violent weather. Every cosmic mystery rests on a single, fragile foundation: the trust in our instruments. Before we can even begin to unravel the contradictions in Deuterium's story, we must confront a fundamental, ground-level question. How do we know the measurements are right? The answer is not simple, and it reveals a hidden layer of uncertainty woven into every date, a point on our maps. This is the instrumental calibration hurdle, and it haunts every observation we make. The challenge is rooted in the very nature of light. To measure deuterium, we do not see it directly. We look for its ghostly fingerprint in the spectrum of a distant quasar or a cold cloud, a specific, minuscule dip in the light at a precise wavelength. But deuterium's signature is not alone. It sits impossibly close to the much stronger, broader dip created by regular hydrogen. For a telescope like Hubble, peering across billions of light years, distinguishing these two lines is like trying to hear a single, quiet violin note played right next to a roaring jet engine. The two signals are almost, but not perfectly, superimposed. The slightest miscalibration in the telescope's optics, or a tiny shift in its instruments over time, can smear these lines together, making it look like there is more or less deuterium than actually exists. This is not a one-time fix. Every observation of every cloud requires its own meticulous calibration against known cosmic landmarks, like the light from specific stars, to ensure the wavelength scale is perfect. But what if the landmark itself has a subtle flaw? Or what if the interstellar medium the calibration light passes through on its way to us has its own hidden deuterium, contaminating the reference? The problem becomes exponentially harder with radio telescopes like a LMA, which observe the cold molecular clouds. Here, we are not looking at absorption, but at emission, the specific radio hum of a molecule like hydrogen deuteride. The signal is incredibly faint, a whisper from the void. To detect it, astronomers must combine the data from dozens of individual antennae, a process that requires exquisitely precise timing and alignment. A timing error of a fraction of a second, or a minuscule misalignment in an antenna's position, can introduce artificial noise or shift the perceived frequency of the signal. This can make a real deuterium line appear weaker, stronger, or even vanish entirely from the processed data. The calibration process for these instruments is a science in itself, a constant battle against the heat of the sun, the vibration of the wind, and the inherent drift of electronics. So when we see that chaotic scatter in the deuterium data, that patchwork quilt of high and low values across the cosmos, we must ask a sobering question. How much of that scatter is real cosmic variance, and how much is simply the accumulated sigh of our imperfect machines, a faint echo of our own struggle to see clearly? Some of the most puzzling outliers, the measurements that defy all models, might not be cosmic mysteries at all. They could be calibration ghosts, artifacts born in the complex interplay of starlight, optics, and software. This does not invalidate the mystery, it deepens it. It means that to find the true signal of the universe, we must first learn to hear our own instruments breathing, and to subtract their heartbeat from the song of the stars. The most detailed maps of stellar nurseries are now revealing a chemical chaos we never predicted. astronomers have begun using powerful arrays like the Atacama Large Millimeter Array to create high-resolution maps of deuterium fractionation across individual molecular cloud cores. They do not simply take one measurement for the entire core. Instead, they scan across it pixel by pixel, building a chemical portrait of where heavy molecules like DCO+ are concentrated. The expectation was a simple, elegant gradient. The core's heart should be the coldest, most shielded place, where fractionation runs wild, creating a bright central peak of deuterium enrichment. Moving outward toward the warmer, more turbulent edges, the signal should gradually fade. This is the clean, radial pattern our textbooks predicted, but the actual maps tell a different story entirely. They show a splotchy, irregular tapestry. Islands of intense deuterium enrichment appear not just at the center, but offset, or in unexpected filaments. Conversely, some parts of the deep interior show surprisingly low values. The pattern does not follow temperature or density in a straightforward way. This is the molecular cloud core map mismatch, and it is a direct challenge to our picture of these cradles as serene, slowly collapsing spheres. The chaotic chemistry points to a hidden architecture of motion and force. A core is not a static lump of gas. It is a dynamic entity, likely spinning slowly, with gas spiraling inward along complex magnetic field lines. These internal dynamics are the invisible sculptors of the chemistry. Imagine trying to stir a cup of coffee with a spoon. The cream does not mix in a smooth, radial gradient from the center out. It creates swirls, vortices, and tendrils. In a molecular core, the infalling gas is that cream, and the deuterium-rich molecules are the tracer dye. Regions of rapid infall might bring fresh, less processed gas into the heart of the core, diluting the deuterium signal in a specific zone. Conversely, a strong, localized magnetic field could channel material, creating a focused stream where fractionation has extra time to work, resulting in a bright, off-center knot of enrichment. Even the subtle warmth from a deeply embedded, still invisible protostar can create a local hotspot that suppresses fractionation, punching a hole in the expected chemical map. These maps are forcing us to see cores not as simple chemical reactors, but as weather systems. They have fronts, currents, and calm zones, all shaped by the interplay of gravity, rotation, and magnetism. Every patch of unexpected chemistry is a clue to the core's hidden history and its future. A splotchy map may indicate a core that is not one monolithic collapse, but a collection of smaller fragments beginning to coalesce, each with its own chemical story. This mismatch means that the deuterium fingerprint inherited by a future star and its planets is not a single number, but a complex average of these swirling, chaotic chemical zones. The planet-forming disk that eventually condenses from this core will blend these disparate patches together, meaning the final chemical identity of a solar system is decided not by a uniform process, but by the specific, turbulent weather inside its birth cloud. This chemical chaos in stellar nurseries is a modern mystery, but it echoes a far older one written in the first 3 minutes. Deuterium is not the only element forged in the Big Bang's fleeting furnace. Alongside it, the universe cooked up the first light metals, helium, and a tiny trace of lithium. And here, we find a second cosmic ledger that refuses to balance. The predicted primordial abundance of lithium-7 is about 3 times higher than what we actually measure in the atmospheres of the universe's oldest stars. This is the lithium problem, a decades-old puzzle that has stubbornly resisted every conventional fix. What makes this so fascinating is that deuterium and lithium are chemical cousins, born in the same instant from the same nuclear processes. They are linked by the fundamental physics of the Big Bang. This means you cannot tamper with one without affecting the other. Any theoretical adjustment made to solve the lithium problem sends a ripple through the entire calculation, inevitably shifting the predicted abundance of deuterium as well. Some of the most exotic solutions proposed for the missing lithium involve new physics from the universe's earliest moments. One compelling idea is the decay of hypothetical particles, like strange neutralinos from supersymmetry, in the first few minutes. As these particles decayed, they would have injected extra energy and particles into the primordial soup, subtly altering the nuclear reaction rates. This could have suppressed the production of lithium-7, bringing the theoretical prediction down to match the frustratingly low observations. But here is the catch. That same injection of energy would have also meddled with the delicate chain of reactions that created deuterium. It could have destroyed a little more of it, or perhaps produced a bit less from the start. The effect might be small, a shift of just a few percent in the predicted deuterium abundance. Yet in the high-precision world of cosmology, where we are arguing over fractions of parts per million, a few percent is a monumental change. It could be enough to resolve some of the tension between the highest precision deuterium measurements from the Lyman alpha forest and the pristine Big Bang prediction. Or it could make the disagreement worse, deepening the mystery instead of solving it. This creates a beautiful and maddening interdependence. Astronomers searching for the answer to the lithium problem must constantly check their work against the deuterium data. A proposed solution that fixes lithium but wrecks the beautiful agreement we sometimes see with deuterium is immediately suspect. Conversely, a new, ultra-precise measurement of primordial deuterium could rule out entire families of theories devised to explain the missing lithium. The two mysteries are locked in a gravitational dance, each one constraining the possible solutions for the other. They force us to see Big Bang nucleosynthesis not as three separate puzzles for hydrogen, deuterium, and lithium, but as a single, integrated event. A flaw in our story of creation must account for all the evidence simultaneously. The lithium problem whispers that our picture of the universe's first moments is still incomplete, that some subtle ingredient or process is missing from the recipe. And whatever that ingredient is, its signature is written not just in the missing lithium of ancient stars, but in the contradictory, scattered map of heavy hydrogen across the entire cosmos. To find it, we must listen to both whispers at once. That deep link between deuterium and lithium points to the universe's original recipe. But what if that same heavy hydrogen could also write the recipe for life itself? This brings us to the most profound hope hidden within the mystery, the idea of deuterium as an astrobiology signature. On our own planet, life is not a passive passenger in chemistry, it is an active editor. Biological processes, from the workings of a single cell to the global cycles of forests and oceans, have a subtle but measurable preference for lighter atoms. When organisms build their tissues, they tend to select regular hydrogen over its heavier cousin, deuterium. This leaves a faint but distinct fingerprint, a slight depletion of deuterium in living matter compared to the surrounding environment. But the reverse can also be true in the complex breakdown and reformation of organic molecules. Some processes can concentrate deuterium, creating pockets of enrichment. On Earth, these biological fractionation effects are small, just a few percent. Yet, in the vast and strange canvas of exoplanet atmospheres, could a massive, unexplained deuterium enrichment be a screaming signal of biology? Imagine a world where life has not just evolved, but has fundamentally hijacked planetary chemistry for billions of years, amplifying that subtle preference into a global atmospheric signature. The hope is intoxicating, a direct way to search for life by reading the weight of hydrogen in alien air. But the cosmic detective knows better than to trust a single clue. This is where every unexplained deuterium mystery we have explored collides with that hope, creating a profound challenge of false positives. An exoplanet atmosphere showing extreme deuterium enrichment would stop any astrobiologist's heart, but the celebration would be premature. We would immediately have to ask, is this biology, or is it geology, or even astronomy, mimicking the signal? Remember the vanished oceans of Venus, its deuterium enriched 100-fold by simple atmospheric escape. A desiccated rocky world could bear that same scar without a single microbe. Recall the protostellar jets, spraying deuterium-heavy water forged in cold space or violent shocks. A water-rich world pummeled by such enriched comets could inherit its heavy hydrogen from a sterile bombardment. Think of Titan, its methane heavy with deuterium, possibly from a hidden subsurface ocean's chemistry, a process called serpentinization that requires no life at all. The dense molecular clouds and prestellar cores show that the universe is a master chemist, capable of generating staggering deuterium enrichments through pure physics and patience in the dark. A young planet forming from such enriched material would simply be born with a heavy hydrogen atmosphere. The very mystery we are trying to solve, the 30 unexplained cosmic abundances, becomes a catalogue of cosmic false alarms for the search for life. Distinguishing a true biosignature from this cosmic noise is perhaps the ultimate puzzle. It would require not a single measurement, but a symphony of them. We would need to understand the planet's context, its star, its orbit, the presence of other atmospheric gases that only life could maintain in tandem. A deuterium spike alongside an abundance of oxygen or methane, in a pattern that defies chemical equilibrium, would be far more compelling. The hope, therefore, is not that deuterium alone will be a simple green light for life. The hope is that it becomes a powerful new word in a much larger chemical sentence we are learning to read. In a universe filled with heavy hydrogen from 1,000 natural processes, the signature of life will not be the presence of deuterium, but its specific pattern, its context, its improbable story written against the noisy background of cosmic chemistry. Finding life will mean listening for a faint, coherent melody in a galaxy that has been shouting in deuterium for 14 billion years. The final answer to this 30-part mystery will not come from a single telescope, but from a new generation of eyes trained on the cosmos. Our story is poised on the edge of a revolution in cosmic chemistry, driven by machines now soaring through space and others being carved from mountainsides. The James Webb Space Telescope, with its unprecedented infrared sensitivity, is already rewriting the rules. It is not just looking for water in exoplanet atmospheres, it is hunting for the specific, subtle signature of heavy water. Detecting that faint fingerprint around a rocky world in the habitable zone would be a monumental leap. It would give us our first direct measurement of the deuterium ratio in an alien ocean, allowing us to ask if that water is primordial, cometary, or processed by a hidden geology. Beyond planets, Webb is peering into the hearts of the earliest galaxies, studying the Lyman alpha forest with a clarity Hubble could never achieve. It has the power to finally see if the shadow of reionization is real, to measure whether the first starlight truly burned away the universe's heavy hydrogen, settling a cosmic debate that has lasted for decades. On Earth, a new giant is rising. The European Extremely Large Telescope, with a mirror nearly 40 meters across, will act as a cosmic microscope for our own galaxy. It will dissect individual stars within dense clusters near the galactic center, measuring their atmospheric deuterium with stunning precision. This will finally map the true gradient of depletion, not in broad gas clouds, but star by ancient star, telling us exactly how stellar processing has sculpted our galactic neighborhood over billions of years. It will peer into the chaotic hearts of protoplanetary disks, watching deuterium-rich ices vaporize and mix, giving us a real-time view of how a solar system's chemical identity is set. But the most definitive answers may come from rocks we can hold. Future sample return missions are the ultimate ground truth. Imagine a probe diving into the plume of a comet like 67P, capturing not just dust, but ices sealed since the dawn of our solar system, and bringing them back to labs on Earth. Here, free from the limitations of remote sensing, scientists could perform isotopic analyses of breathtaking precision, decoding the exact deuterium signature of that comet's water, and perhaps finally pinpointing which family of icy bodies delivered our oceans. A Mars sample return mission carries similar promise, a core drilled from the polar layered deposits. That frozen climate diary could be sliced into thousands of thin layers. Each slice, analyzed in terrestrial labs, would reveal the deuterium ratio of Martian water from a specific year, millions of years in the past. This would not be a single number, but a high-resolution climate record, showing us the precise timing and violence of Mars's great drying spells. These missions represent more than better data. They are keys to unlocking a unified theory. They will connect the dots between the primordial abundance, the chaotic chemistry of dark clouds, the violence of star formation, and the final composition of planets. Every anomalous measurement, every outlier in our 30-part mystery, is a target. The scatter in the data is not noise, it is a map, and these new instruments are giving us the legend to read it. The story of cosmic deuterium is not a closed book from the past. It is a live document, and the next chapters are being written right now, in clean rooms, in mission control centers, and in the silent gaze of mirrors pointed at the dawn of time. The universe left a fingerprint in heavy hydrogen, and we are finally building the magnifying glass to see its every whorl and ridge. This heavy hydrogen is not just one clue, it is an entire language. Every deviation from that pristine Big Bang number, every spike and dip across 30 cosmic crime scenes, is a sentence written in the grammar of physics, chemistry, and time. To read it, we must understand that deuterium is the universe's ultimate multi-purpose tool. It is a thermometer from the first 3 minutes, a forensic tag for galactic recycling, a chemical witness to planetary birth, and a speculative signature for worlds beyond our own. The grand synthesis is this: no single story can contain it. The same isotope that confirms our most elegant theory of cosmic origins also reveals the breathtaking, messy complexity of everything that came after. It traces the journey of a galaxy from its first sip of pristine gas to its maturity as a churning engine of stars and metals. It records the violence of stellar nurseries and the patient chill of interstellar clouds. It is etched into the vanished oceans of Venus and the hidden sea of Europa, a chemical ledger for water lost and water waiting to be found. This is why the 30 mysteries persist, not as failures of our understanding, but as proof of the universe's layered creativity. Deuterium is not a problem to be solved with one equation. It is a narrative to be followed across 14 billion years. We are learning that the universe uses this heavy hydrogen to write its history in 1,000 different scripts, from the nuclear physics of creation to the delicate chemistry that might one day whisper of life. Our task is not to force the data into a single, neat box, but to become better translators, to listen for all the stories this one fragile atom is trying to tell us at once. Deuterium's story is a cosmic detective novel with 30 chapters, each one a contradiction that refuses to be ignored. We have followed this heavy hydrogen from the pristine furnace of the Big Bang into the chaotic kitchens of star formation, across the vanished oceans of dead worlds, and into the icy hearts of distant comets. At every turn, it defied our expectations, refusing to settle into a single, simple narrative. Yet within that defiance lies its true power. This tiny isotope is not a broken piece of the puzzle. It is the most versatile diagnostic tool in all of cosmology and astrophysics. Its abundance is a question that echoes across every scale of existence. It tests our models of the universe's explosive birth. It maps the hidden weather inside galactic clouds, and it writes the chemical biography of every planet we will ever discover. To understand, Deuterium is to hold a key that unlocks multiple doors, from the nuclear physics of the first second to the delicate chemistry that might one day whisper of life on a distant, watery world. The journey does not end with 30 mysteries, it begins with them. Each unexplained measurement is a signpost pointing toward a deeper layer of cosmic truth we have yet to uncover. What is your favorite Deuterium puzzle from this cosmic tour? Was it the ghost oceans of Venus, the chaotic comets, or the violent jets of newborn stars? Share your thoughts below, and if you are fascinated by the hidden rules of our universe, subscribe for more deep dives into the greatest space mysteries.